today's video, we'll be finding electric field due to conducting solid sphere, right? And potential as well. Okay. See, this term conducting solid sphere. Okay, this is actually a quite confusing term. Okay, for electric field, this term solid conducting sphere. Okay, then again another term for this, or you can say that electric field due to solid conducting sphere. Okay, then due to hollow conducting sphere, and another hollow non-conducting. Okay, electric field due to all these three distribution is actually same. Okay, so for all three we will finding electric field and it will be common, and potential as well. Okay, so if you look, this is actually, you can say, conducting solid sphere or conducting hollow conducting sphere. Okay, see, for conducting sphere, you know that I think I have not covered conductors. Okay, so basically the charge for the conductors, they all get distributed on the surface. Okay, either be it non-conducting or conducting, right? Charge gets distributed on the surface. Okay, so we'll find electric field. See, we'll find electric field in three regions. Okay, let's say this is actually of radius r. Okay, so we'll find inside, we'll find on the surface, and we'll find outside the surface, right? We'll find first inside the, just a second, we'll first find inside this, then we'll find at the surface, and then we'll find at the outside. Okay, so the first is when small r is less than capital R, that means uh, inside the sphere. Okay, so you know that if you consider another sphere, okay, of radius smaller, right? And if you consider an area element dA here, right, pointing upwards. Okay, what will be the flux? Okay, what will be the flux passing through this small sphere? It will be d phi. If you say, if you tell that elemental flux through this area, it will be d phi is equals to E dot d, right? And we know that this E dot dA will be, that means flux is equals to E dot d, right? This closed integral. Okay, so flux will be E into 4 pi small r square, right? And by Gauss law, what we have obtained, that this flux is actually Q enclosed upon epsilon naught, right? So what you see Q enclosed here, since all the charge distributed are at the surface of the sphere, so this Q enclosed, that is the charge enclosed inside this sphere of radius small r, if you say this radius smaller, is actually 0. That means Q enclosed is actually what? 0. There is no charge inside this radius of small r. Okay, radius in this sphere of radius small r, right? So from here you will get phi is equals to 0. Okay, so this is equation 2 and this is equation 1. Okay, so from 2 and 1, what you get? You will get E into 4 pi r square is equals to 0. So this cannot be 0, this cannot be 0, this cannot be 0. Okay, so electric field is 0, okay, inside the sphere, okay, inside the conducting solid sphere, right? Now we'll find when small r is actually equals to capital R, right? The second, so when small r is actually equals to capital R, okay, we just need to manipulate one term, okay. See, just a second, we'll first find for small r greater than capital R, okay, then we'll just substitute one thing, okay, when small r is greater than capital R, that means if it is our sphere, right, of radius r, then we need to find electric field at this point, right? So we'll apply the same approach here, right? We'll first draw a sphere of radius smaller, right, and we'll find flux through it, okay. So the flux through area element, if we consider an area element dA here, okay, the flux through this will be E dot dA, right, then phi will be E, this surface integral dA, that means E into 4 pi small r square, this is actually phi, okay. And in this question, this distribution charge, okay, this charge distribution, the net charge on this sphere is actually capital Q, okay, on the original sphere. So charge on this will be capital Q, right? So by Gauss law, okay, by Gauss law, what you get? You will get flux phi is equals to Q enclosed upon epsilon naught. Okay, what is Q enclosed here? This is actually, if you see, this whole charge capital Q, that is on our original sphere, is actually Q, and this whole charge is enclosed within the sphere of radius smaller, okay. You can see by this figure, okay, this whole charge is enclosed under this radius, this sphere, okay. So Q enclosed will be the charge on the original sphere, Q upon R, sorry, Q upon epsilon naught, okay. uh, we have got this, okay. So this is equation 2 and this is 1, we just need to cure these, okay. So from here you get E is E into 4 pi R square is equals to Q upon epsilon naught. So from here you get E is equals to 1 upon 4 pi epsilon naught Q upon R square. This is actually the electric field at outside the hollow conducting sphere, or you can say conducting solid sphere, or hollow non-conducting sphere, right, outside. Now our third case, when small r is equals to capital R, that is at the surface, okay. So at the surface we just need to substitute one thing, okay. I think we have yes, we have got the electric field, okay. We just need to substitute this small r by capital R, which is original radius of the sphere, okay. So electric field will be 1 upon 4 pi epsilon naught into Q upon capital R square, right. This will be the electric field, okay, original electric field, okay. So we have find it for inside, for outside, and the surface for a hollow conducting and other things, okay. From here you can also see one thing, okay, which I have told you near a in the previous video, or before 1 or 2 videos I have told you electric field near a conducting surface, okay. So if you look at this, this is 1 upon 4 pi epsilon naught. If you consider this surface as sigma, okay, having surface charge density sigma, okay, then this Q will be what? It will be sigma into 4 pi r square upon r square, okay. This electric field near this, okay, at the surface, okay. So 4 pi gets cancelled out, okay, r square gets cancelled out, and you will get sigma epsilon naught. And we have got this electric field over there as well, okay. and this will be what maximum, right? So this is all about